Thank you, Elizabeth. Hello, everyone. Delighted to be here again. My name is James O'Donnell, and I'm the reporter for AI and hardware at MIT Technology Review. This chapter is called The New Compute, and in my reporting on AI, I come across plenty of computing evangelists, and by that I mean people who think that to accomplish the breakthroughs that tech optimists promise, like more intelligent AI models and faster drug discovery, what we really need are breakthroughs in computing, so better and faster chips, new architectures for those chips, and the like. Then there are also plenty of skeptics who say that this unrelenting hunger for more computing power is just requiring massive amounts of energy and adding to our reliance on fossil fuels. And so this session, in some ways, is about squaring those two things, about squaring the promise of new computing technologies with the risks. To kick us off, my first guest is Pete Shadbolt. He's a quantum computing expert, as well as co-founder and chief scientific officer at PsiQuantum. As a reporter, I've noticed that the field of quantum computing really draws a peculiar pool of talent. I really think of them as the underdogs, even though I don't say that to them directly, because if you sign up to work in quantum computing, you're choosing to work on the cutting edge, yes. You're building a technology that could revolutionize the speed at which we conduct science, but you're also signing up to build a technology that might not be useful until after you retire or decades to come. So that makes the quantum people really fascinating to talk to, and our guest, Pete Shadbolt, is no different. Pete earned his PhD in experimental photonic quantum computing 10 years ago, and he's been pushing the field forward since then, leading the charge of a unique approach to making quantum computing possible. I'm thrilled he's here to guide us on the latest breakthroughs in the field. So Pete, welcome to EmTech. Stage is yours.
Brilliant. Thanks so much, James, for the really nice introduction, and thank you so much for having me at this wonderful conference. I'm Pete, I'm a co-founder of PsiQuantum, and today I'm just going to try to give an overview of work that we do at the company and progress that we're making towards useful quantum computers, and also just try to put that in context a little bit. I want to start with this image. This is a favorite image of mine. It's a picture of a black hole. You can see the event horizon and the accretion disk. If you've seen the movie Interstellar, you might recognize this image, which is pretty scientifically accurate and beautiful in my opinion. This is a special image because it was made 40 years ago in 1979 on an IBM punch card-based computer. And of course, those machines didn't have a display. So you might ask, how was this image made? This was a French gentleman, Jean-Pierre Lumière, who must have spent a long time feeding punch cards into the computer, taking numbers out, and then he had a big canvas and a paintbrush and India ink, and he painted each point onto this figure one by one. It must have been pretty amazing back in 1979 to see this image appear. To me, this is a testament to the power of seemingly primitive computers, and it's also a metaphor for how I think about quantum computing, which is that for a long time, we've understood that quantum computers would be able to solve valuable problems that we will never solve using any conventional supercomputer that we could ever build. And that promise has sucked in the lives of tens of thousands of our best scientists and engineers and billions of dollars of capital. And quantum computing still has this amazing gravitational pull and almost kind of inevitability to it. I think there's a pretty good analogy with the way that things have gone with machine learning. There are people in this room who will remember when machine learning was going through winters and even times when you wouldn't admit to being an AI researcher because the field was so damaged and so long running. Of course, all of the excitement that we see around AI right now is the product of a giant field of research, many thousands of people. But I also think that there's a pretty defensible argument that it was really just a few papers in recent years that ended up swinging billions of dollars of capital and creating the world's most valuable company and all of the froth and excitement that we see today. And I think that quantum computing has a similar kind of trajectory where of course it is the product of a huge field of research, quantum physics and information theory and so on. But I also think there's a case that it was really just a few papers, 1995, 1996, and 1997, papers that came out of Cambridge and Boston and MIT, that ended up swinging billions of dollars of capital and putting people like myself and my co-founder Jeremy on lifetime journeys to try to realize this technology. That journey has taken us here. This, in my opinion, is the most impressive quantum computer that exists. This is Google's system in Santa Barbara. Most of what you see in this image is a fridge that is cooling the chip to 1/100th of the temperature of deep space. So Google take the chip, they cool it down to minus 270 degrees Celsius to deep space temperature, and then they cool 100 times colder again. At the bottom of that fridge is a single chip that would fit in the palm of your hand. There are about 100 qubits on that chip. And on the one hand, that system is amazingly impressive. That single chip today can win a race with a $1 billion building scale supercomputer, unequivocally by a very large margin. And so that, to me, is a very profound demonstration of the exponential promise of quantum computing. But it's also the case that if you listen to the CEO of Google, NVIDIA, IBM, or Microsoft here, you can see that they all understand that to realize the useful commercial applications of quantum computing, finding new drugs, new materials, new catalysts, new fuels, and in general kind of gaining mastery over chemistry, physics, and math, in order for us to access that useful regime, we're going to need error correction, and we're going to need much bigger quantum computers. And by much bigger, I mean about 1 million qubits relative to the 100 that Google have today. Not only do these guys know that they need big systems, but they're actually now starting to take tentative steps towards data center scale, million qubit, fault-tolerant quantum computers. If you read between the lines of these images, you can see that these organizations are now getting serious about large systems. And I think that's a very exciting point to be at. My organization, PsiQuantum, has been singularly focused on realizing a very large million qubit fault-tolerant quantum computer from the very beginning. All of our resources, all of our time over the last 8 years have been exclusively devoted towards this target. This is a sketch of the machine that we're building. And starting on the left, we're using microscopic photonic components that we essentially borrow from the telecom industry. So telecom guys figured out how to move light around on a lithographically fabricated silicon chip, and we repurpose those microscopic photonic components to manipulate single photons, particles of light, which we use to encode the qubit. Most of those components are classical, with the exception of the superconducting single photon detector that we need to detect single particles of light. Those components are built into a chip. The chip is packaged into a module that is mass manufacturable in much the same way as cell phones or optical transceivers for data centers. And then we're going to need thousands of these board-level assemblies to give us a useful system. So we rack them up into these cryogenic cabinets that you see in the fourth column here. These are the equivalent of a 19-inch rack that you'd find in a data center, but they are cooled to liquid helium temperature. And I'll say more about those cabinets later on. We're going to need many of those cabinets to give us a full-scale system, and that will be networked together with telecom fiber and resembling a conventional supercomputer in many ways. As far as where we're at in this picture, we've made and tested tens of millions of devices. We've made thousands of wafers of silicon, hundreds of these board-level assemblies. We have one cabinet running in the UK, and we just took receipt of a much larger cabinet that is now at the Stanford Linear Accelerator. And then just recently, we announced 2 sites in Australia and in Chicago where we will build utility-scale systems. And we'll start to break ground on those sites in 2025. The theme across this entire picture is that we are seeking as much as possible to leverage high-volume manufacturing, from the semiconductor chip to the package and even to the cabinet, which is built by a company who normally builds fridges for the food and beverage and pharmaceutical industry. I'll say more about that in a second, but I want to take a tour from left to right in that figure, from the microscopic components to the big stuff. Right now, we make, as I said, thousands of wafers of quantum chips, so dinner plate-sized silicon wafers. If you were to look inside those wafers, these are the components that you'd find. On the left, you see the silicon waveguide, where we carry single photons. We have thermal heaters, which interestingly get to a few hundred degrees Celsius, so well above boiling point, despite being millimeters away from superconducting detectors that are operating at 2 Kelvin, so deep space temperature. This green object in the middle is the most exotic device in the chip, and that is a superconducting single photon detector, strictly a quantum device. And then on the right, we have a super low loss waveguide that we've developed, as well as a fast optical phase shifter that we use to control the qubit and basically program the machine. These chips are not built in a university clean room or in a sort of DIY manufacturing context. They're built in this fab. This is GlobalFoundries Fab 8 in upstate New York, and this is a commercial semiconductor foundry in the same category as TSMC, Samsung, and Intel. And this is a great source of pride for me, that we've been able to take exotic technologies like superconducting detectors and single photon sources and take them out of the lab and put them into what is essentially the highest level of maturity of semiconductor manufacturing that exists on planet Earth. You can imagine that this is expensive, but what this gives us is a promise that if we want to build huge numbers of devices with extreme uniformity, that promise is kind of built in to a fab like this. The components in those wafers need to perform well beyond the state of the art. And so we've been working hard to improve component performance across all of these devices. And the overall picture, as you can see here, is that after 4 years of work, in some cases we're now exceeding our target specs. In some cases we're very close to target. In other cases we still have hard work to do. But overall, we have a very compelling argument that we're going to have good enough components well before the infrastructure for the site can be built out. We've taken those components and built qubits, and those are actually being tested in the UK right now. We've shared both those device performance numbers and the qubit performance numbers in this paper, which we recently put on the archive. And the good news is that the numbers are very good. So these are competitive with any other qubit that's out there. But again, the most exciting thing for me is that these are being built in a high-volume semiconductor manufacturing environment. There's been one key component missing, which is an optical switch. It's actually not a quantum device. It's just a classical device for routing light. But we need to do that with performance that's way beyond anything that's available in the telecom industry. And so to do this, we resorted to a new material, barium titanate, which is the strongest electro-optic material known to science. This is a facility in San Jose. When we started, this was an empty warehouse. And we built inside that warehouse this tool, which is the largest molecular beam epitaxy tool in the world to our knowledge. So it's a dual-chamber 300 millimeter MBE tool. And what this is doing is it is fabricating essentially perfect wafers of this barium titanate material. And that's what allows us to move light around at high frequency on the chip. We are now able to take wafers out of that fab in San Jose and heterogeneously integrate them together with silicon at GlobalFoundries. We're building switches. Here you can see images of those wafers with a pretty complex switch on it. That switch is about 2 times smaller than what we need for the first generation machine. So we're getting into the ballpark of the scale that we need. And that switch is really the key for us to be able to start to now build much larger systems. So going from resource state generation and entangled state generation to logical qubits and then to a full computer. As we do this, we're going to run out of cooling power in the chandelier-style fridges that you're familiar with for quantum computing. So these beautiful golden chandeliers have become the kind of emblem of quantum computing, but they've also got problems. They're very limited in terms of how much heat they can dissipate, and usually you can only get one chip into the fridge. So we, a few years ago, laid out a plan to get away from the chandelier form factor, increase the cooling power by a huge fraction, and also massively increase the density so that we can put lots of chips into the same cabinet. And when our team put these nice renders in front of me, I was pretty skeptical, honestly. Like, you're going to do away with the standard way of doing things and scale by an order of magnitude per year for multiple years running. I was a little concerned that they were dreaming, but they've done that. So this is a decommissioned synchrotron accelerator in the north of England, and we're using helium from that facility to test PsiQube that you see there, which was the first non-chandelier cryostat that we introduced for quantum computing. This system has about 10,000 times more cooling power than is available in a Google or IBM chandelier-style cryostat. And you can also see that it contains many, many chips. This is still a development vehicle, and so now we're introducing a production-scale cabinet. This is built in Minnesota, and you can see that it is quite far from the Swiss watchmaking, beautiful, delicate systems that you're familiar with in quantum computing. This is a much uglier, simpler, cheaper, and higher power system that's basically stainless steel fabrication. This is a stainless steel contract manufacturer who builds this for us. You can see from looking at it that it's going to consume a lot of helium. Where do we get that helium from? This is the SLAC LCLS2 cryoplant that's very close to where I live in Menlo Park. This was built to provide helium for the linear accelerator, and we're very grateful to DOE, Stanford, and SLAC for allowing us to tap off helium from this system, and we're actually now building systems inside the LCLS2 facility, and I'll show you that here. So here you can see a big cabinet that's actually plumbed in, and we'll start taking helium later this year. And then DARPA have been running a utility-scale quantum computing program for a few years now, where they're looking at paths to get to large-scale quantum computing quickly. They will start to actually look at this system in 2025 when it turns on. That will be a few thousand photon sources running inside a single cabinet that's pretty close in form factor to the cabinets that will go into our first-generation systems. You can tell from that previous picture also that we're going to run out of space in Stanford. And so a few years ago, we started looking for sites where we would actually build utility-scale systems. And it's very, very exciting that a few months ago, the chief scientist of Australia, the Prime Minister, and various other politicians announced a $1 billion Australian deal for us to build our first system at this site, which is about 1 million square feet of land just outside Brisbane Airport. And we hope to break ground on this site in 2025 and have the site ready by end of 2027. Following up on that Australian activity, which will be our first utility-scale machine, this is a picture of the US Steel factory that used to sit on the south side of Chicago. It used to make 1 million tons of steel a year. And more recently, we've announced, together with Governor Pritzker, that there will be, so this site has sat idle for 40 years. It's greenfield. And we're going to build a $500 million quantum computing campus on that site. PsiQuantum will be the anchor tenant of that activity, although there'll be other quantum computing efforts on the campus. And DARPA is moving both their utility-scale quantum computing program and their quantum benchmarking to this site in Illinois. Both in Australia and in Chicago, we're extremely excited to be able to engage with the extremely well-established quantum computing ecosystems that lie there, as well as expertise in high-power cryogenics, high-energy physics, etc., that's notoriously successful here in Chicago. Before I wrap up here, again, many people here will remember AI struggling over time, and there were times where I think people really doubted that it would ever make it over the line. Of course it did, and that's thanks to both the existence of hardware from unlikely sources like gaming GPUs, as well as a very, very dogged commitment to improving the efficiency of the architectures and algorithms. So this is data showing 7 years of exponential progress, just reducing the resources required for machine learning algorithms. And without this, we wouldn't have all of the excitement that we have around AI today. Here's 20 years of sustained exponential progress just in a single classical algorithm. And we have very much the same story in quantum algorithms. So this is showing public domain data on the resources required to implement quantum algorithms for things like drug design, for catalyst design, for new ways of making fertilizers, for code breaking, and for material science. And you can see exponential progress, which is very encouraging. We need to continue on this trajectory in order for these algorithms to fit into the machines that we're building. And the good news is that we have very good reason to believe that we will continue on that trajectory. So sorry to go over time a little bit here. Suffice to say, I don't do any of this work. I just make the PowerPoint. It's a huge privilege to be able to present the work of the brave people at PsiQuantum, and thank you for your attention. I really appreciate it.
Thank you, Pete. If you want to have a seat, have a little time for questions. I want to start, I assume there are some people in the room who have not followed quantum super closely over the years, and I'm wondering if you could just briefly lay out why is traditional computing not going to be enough? You know, we hear about supercomputers all the time. Why will that eventually reach a ceiling?
Yeah, so machine learning has been very successful in learning from data and making good approximations in areas where we have large volumes of data. However, there are problems that we would like to solve from first principles or in areas where we don't have good access to data. So drug design, materials design, partial differential equation solving. These are the types of problems that we resort to supercomputers for. Many of those problems have the property that they scale exponentially badly as you increase the size of the molecule or the size of the area of material that you're trying to simulate. And so for some of those problems, we don't know of any classical algorithm that would solve those problems in any kind of acceptable time, even with a conventional computer the size of Manhattan or something. So there are a set of problems that we don't expect to ever solve with conventional supercomputers, and that's why people are going to these great lengths and why there is so much excitement about quantum computing. And those problems, of course, can sound a little esoteric, but I kind of like to make the point, if you think about the Fortune 100, to me as a technical person, it can look like a bunch of guys in suits shaking hands with each other, but you know, car company, materials, energy, pharmaceutical, semiconductors, so many of these giant industries sit on a foundation of chemistry, physics, math, materials, and in many cases they're being forced to innovate on those foundations at a much greater pace than they have historically. And so that's, you know, really why I think quantum computing is a pretty exciting prospect.
Yeah, and if you have a question in the room, just go ahead and hold your hand up. We'll probably have time for one at least, and we'll get a microphone to you. But in the meantime, I want to ask you about your approach, because Google took the approach, hey, we're going to do this sort of incrementally.
Yeah.
And as you showed, I think that was a 100-qubit computer, you know, probably not that useful compared to what you want to build. You guys have instead said, the only thing we're going to work towards is the first commercially viable one.
Yeah.
What have been the strengths of that approach, and how has it kind of held you back compared to some of the other quantum people out there?
Yeah, so so first of all, I should emphasize the Google group and many other large efforts in quantum computing and small efforts in quantum computing have done incredible work. And it is amazing that 10 years ago, 15 years ago, it was a huge accomplishment to even have a single working qubit. Today, we live in a world where everyone can make great qubits. You know, 3 nines of fidelity is, you know, nothing to write home about. And there are teenagers today signing into AWS and Google Cloud, running Python on real quantum computers. Like, that's an amazing leap that the entire field has made in the last decade. To explain PsiQuantum's approach, I would draw an analogy that isn't supposed to be derogatory, which is between a toy rocket and building a rocket engine, like a Falcon 9 engine, Raptor engine. So the toy rocket is very satisfying because you light the engine and you see it go up and it flies, and it is in some sense a real rocket. But of course, the engineering associated with building that toy system has very, very little to do with the engineering associated with developing a Raptor engine that can take you to orbit. And PsiQuantum's approach has been much more like the latter. The advantage of that is that we think that we are making efficient use of capital. We spend our resources, our money and time exclusively on the problems that we think are associated with scale. The problem with that is that when you do a rocket engine test, it doesn't go up, which is a little unsatisfying. And so we have to do a lot of communicating to make sure that people understand how that fits into the bigger picture, and also to have intermediate milestones like that 25 system that's going to be running next year, and how those de-risk the systems integration, the scaling, etc. It's a harder story to tell, but we think that's necessary to get to scale.
And we've got about a minute left. One of the most impressive things you showed is just the supply chain that you're building here. I mean, we're talking about cooling things to deep space temperature and the machinery required for that. How are you managing that, and what is the sort of most impressive piece of that supply chain to you in the 50 so seconds we have left?
Yeah, so making stuff that cold is not something most people encounter in their day-to-day life. Firstly, if you look at leadership class supercomputer, you always see the beautiful screens and visualizations and everything that they put on these big machines. What they don't show you is what's underneath in the subfloor, which is all of the water cooling infrastructure that actually looks a lot like that big industrial machinery that I showed earlier. So we're not actually particularly differentiated in having big compressors and big ugly pieces of machinery. They just hide it underground. And then my father is a wastewater engineer, so he did sewage treatment his whole life. And I'm now very proud that I'm starting to build or get involved in large pieces of industrial machinery. It's exciting for me, having previously spent my lab on an optics bench. It's also daunting to see some of the images that I showed from LCLS2 from SLAC. I showed that to my father, trying to impress him, and he said, yeah, you know, compared to the scale of things that they did for, you know, oil and gas, wastewater treatment systems, etc., it's actually not a crazy piece of equipment. So there's 2 points of view on that. One of them is that it's really exciting that quantum computing is now headed into this terrain where it's not just a benchtop experiment. We're really getting serious about building large systems. There's another point of view, which is my dad's point of view, which is, it's nothing compared to stuff we did decades ago. And, you know, obviously both points of view.
Yeah, you will forever wrestle with those. I think that's all we have time for with you today, Pete, but thank you so much.
Thank you so much.
Thanks.
Thanks.